Hi, everyone. Thanks for joining. I'd like to start with a quick question. How many of you found yourselves working hard and doing your very best to train a model, and then after releasing it, realized the real world does not behave as you expected it to? I'm here to talk to you today about where the root of this evil often comes down to. If I have to put it in a single word, it would be unknowns. These unknowns can present a massive challenge to our models since they broaden the gap between our model and the real world. What kind of unknowns am I referring to? It could be anything from a shift in some characteristic of your domain's distribution to a whole new product your company launches, which brings completely new traffic. Today, I will discuss one specific type of these unknowns, a shift in your label's distribution. To put this in real context, let's imagine, for example, that you're interested to train a model to predict COVID. This graph here shows the number of cases identified in Israel daily. Imagine you train a model to predict whether a patient is COVID positive based on March 2020 data, and then apply it at September 2020. How would you imagine your model will perform? Not at all ideal, right? It will probably underestimate the probability that a patient is COVID positive simply because the reality the model knew while it was developed is so different from the new reality it is now being used at. What if instead of leaving all the hard work for when our model crashes upon reality, we could challenge ourselves while our model is still in development? Imagine we could train our models at advance to be less susceptible to these changes, not by coincidence, but by design. I owe you an introduction. So, my name is Nofar, and I'm a principal data scientist at PayPal. Today, I'll share with you such a use case I encountered while training a model to identify fraudulent logins performed at PayPal. We will discuss different approaches I examined and what was their effect when tested during one of these unknowns. Hopefully, by the end of this session, I can not only present to you how your model can be more agnostic to these unknown changes, but also provide you with practical approaches you can apply to your model. So, as briefly mentioned, at one of my recent projects, I worked on training a model that will predict the riskiness level of a login performed at PayPal. I perfectly aligned with my model's end users on their current pains, made sure I'm using every possibly useful feature, performed hyperparameter tuning, trained a deep neural network, and after a thorough research, I eventually had in hand a model I felt confident releasing to the real world, only to find out a few weeks later that I'm way off. An unexpected change at my end user's domain yielded a monumental change at my label's distribution. This obviously caught me off guard, both me and my model, which did not perform exactly as I was hoping it to. How can I help my model be better prepared for the real world's unknowns if they're unknown? At this point, and with these questions in mind, I started a journey to explore how I can do things differently. Along the next 10 minutes, I will tell you about two different paths I took while exploring possible solutions to this problem. One, based on my understanding of the domain I worked on, and another, based on what recent research in the field suggests. These approaches had some advantages and disadvantages, so I will then also detail a third approach I examined that will combine the first two. I will use COVID prediction to explain what I've seen and experienced in my research on fraud domain. So let's start with the domain-oriented approach. The first thing I did was to explore the different cases in which a label distribution shift took place in the past. I wanted to better understand what caused these shifts and see if this understanding can maybe lead me to a relatively quick fix for this problem. While diving into these cases, I managed to identify several different types of scenarios that yielded a label distribution shift and could potentially repeat themselves in different variations in the future. In each of these scenarios, certain types dominated, or in other words, much of the distribution shift was among them. I then used my domain knowledge and my model's end users' domain knowledge to identify different types of positive labels. What do I mean by different types? If we use our COVID prediction as an example, it could be, for example, identifying positively tested patients with background diseases, older populations, younger populations, and many more. I decided to use this distinction between the different types of positive labels and train a model that focuses on each of these different types separately. What I practically did was train a model that uses the entire data set for several epochs, then kept training it to specifically focus only on one of these types for several epochs, then a few more epochs focusing on another, and so on and so forth. Another thing I did was overweight the positive labels, my minority class, differently every several epochs. What I was hoping to do is teach my model different possible scenarios of changing label distribution among these different types. I trained the model according to this approach and tested it for the two examined timeframes seen earlier. One, which behaves similarly to what my model knows from its training timeframe, and one that presents a shift. I found that it managed to perform slightly better than when a label distribution shift took place, but not better than my original model for the known distribution. I felt like I might have confused my model maybe with various different possible scenarios, and that what it actually needs now is a hint indicating which of these scenarios now dominates. What's a better place to look for that hint than the road not originally taken? So at this point, I decided it is a good time to explore what existing approaches suggest. I found not enough, but still quite a few researches targeting this field of label distribution shift. There are several different approaches I encountered which aim to estimate label distribution shift and either use it to retrain a model or correct the score of an existing one. I will focus on one of them today, and in a few moments, you will understand exactly how it assisted to provide much of this needed hint. The authors of the work I'll focus on today present a simple and easy to apply approach based on maximum likelihood. This approach aims to correct the score of a previously trained model to a new shift. To be more precise, they suggest an important addition to a previously introduced approach. This addition removes the reliance on a very limiting assumption that the model is calibrated. And therefore, this addition assists this approach to outperform existing approaches, even for modern neural networks, which tend to not be calibrated. As mentioned earlier, I trained a deep neural network, so this addition was very much needed in my use case. Great, so following this very high level intro, let's start with some basic definitions before we deep dive into this approach. We'll use Y to denote our classes commonly used. In our COVID example, it would indicate whether a patient is positive or negative to COVID. P of Y will denote the proportion of patients that belong to class Y in the source domain. March 2020, for example, which is when we'll pretend we trained a COVID prediction model. We'll use Q of Y similarly for the target domain, September 2020, which is when a significant shift took place. P of Y given X will denote the conditional probability that a patient belongs to class Y given symptoms X are features at the source domain, and Q of Y given X will denote the same for the target domain. So according to the author's approach, we'd like to perform two steps. First, estimate the size of the shift, then use it to adjust our existing model score. Practically, what we need to do is estimate Q of Y to P of Y, or in other words, estimate the size of the shift, meaning the label distribution at the target domain comparing to the distribution at the source domain. And then use the formula mentioned here, which is based on Bayes' rule, to estimate what our model should predict for the target domain, Q of Y given X. We will use our originally trained model, which will yield P of Y given X, and adjust it to the target distribution using the estimation performed at the first step. We will use these two steps to perform an iterative process, which I will detail in the next slide. And by the end of this iterative process, we will be able to correct our model score and adjust it to the new label distribution. As mentioned briefly, the formula detailed at the second step is based on Bayes' rule with the use of some adjustments that are valid, assuming that this is indeed a label distribution shift. In other words, we're assuming here that the shift we're seeing is indeed a shift in the label distribution and not in the relation between X and Y, for example. If the latter is the case, then this could be a concept drift or any other type of data set shift, which is out of today's talk scope. But I wanted to point out that these cases can and should be treated differently. So we can all agree that every component of this equation can either be calculated by the model, which we have in hand, that was trained on the source domain, or used from the estimation performed at the first step, right? So what you're probably asking yourselves now, and rightfully so, is, but wait, Nofar, how do you estimate the size of the shift? Your entire talk is about Q being unknown. So let's talk about this iterative process and then simulate its implementation using a toy example, and I promise all your questions will be answered. And if you follow along the upcoming 2 minutes, I promise you got this. So one suggestion by the authors is the following. Let's start by guessing what Q of Y is. A pretty good place to start is assuming that Q of Y equals P of Y. In order to do that, you can use your model to classify a data set from the source domain, average its results to estimate P of Y. Then, as mentioned, set Q of Y to be equal to P of Y. Now that we've initialized some parameters, we can use what we have in hand to estimate Q of Y given X using the formula we saw earlier. In order to calculate P of Y given X at the formula, use your model again, but this time on top of a target domain data set. So now we have in hand an initial estimation for Q of Y given X. But wait, we don't have to stop here. We can now average Q of Y given X and use that to improve our estimation for Q of Y. This new estimation for Q of Y can be used to estimate a new Q of Y given X, and we can keep doing that until our estimations for Q of Y converge. As briefly mentioned earlier, your model should be calibrated for this procedure to work. So the authors suggest a calibration method which showed very satisfying results. It will remain out of this talk scope, unfortunately, but please remember calibration is needed here. The authors also recommend to implement this approach using Python abstention package, which implements all of the relevant steps seen here, including model calibration. Curious to know how this iterative process looks like? Let's take a look at an illustration based on a COVID prediction toy example. This example is taken from a blog post written by one of the authors of the paper I focus on here today. So according to this toy example, our source domain has 10% COVID positive cases, and the target domain has shifted all the way to 70% positive. So we'd like to begin this iterative process at 10% and converge somewhere close to 70%. What we're seeing here is a stacked bar chart of the portion of positive and negative cases in orange and blue, respectively, across disease score. This disease score is our model's single feature for this toy example. So the red curve is the positive fraction in each bin of our feature, and it presents how our model's prediction would distribute across disease score at the source domain. We will now score a target domain dataset using the model we have in hand, which was trained on the source domain. So at this point, what we'll soon have in hand is what the original model naturally predicts for the target domain. As you can expect, it underestimates the positive cases, but it estimates more than 10% overall. In fact, it predicted 34% of the cases to be COVID positive, as can be seen by the dashed curve the red dashed curve. So 34%, that will be the first iteration's new estimation for Q of Y heading towards the second iteration. At the second iteration, we can use the model again to correct its score using our recent estimation for Q of Y, which is 34%. When we'll do that, we'll find our model classified 53% of the events as positive, and that will be our new estimation heading towards the next iteration. The writers repeat this procedure for a few more iterations until the seventh yields a converged estimation of almost 70%, which is, as you know, actually the true target domain label distribution. Their paper shows that this works well, not only for a toy example with a single feature, so rest assured. Remember, excuse me, remember that I mentioned earlier I was looking to provide hints to my model. So this has much of what I was looking for, being able to tell my model, hey, remember when we trained you back in March, you had only a few hundreds of positive COVID cases a day? Well, now it has increased all the way to a few thousands per day. Adjust yourself accordingly. So I went ahead and applied this approach and learned that it managed to achieve pretty good results overall, both for the original distribution and for the shift. The problem is when looking into the different scenarios I identified when originally following the domain-oriented approach, since this correction that I just presented to you adjusts the model similarly for the entire population. So going back to our COVID example, imagine only people over 60 years old would be infected more of COVID while the rest of the population remains as it was. In this case, I would basically adjust my model to predict teenagers are more likely to get infected while they aren't. And on the other way around, teenagers would make me underestimate how likely it is for older populations to get infected. An additional problem with this approach is from a practical perspective. We're basically talking about maintaining two models in production, or more accurately, a model and a procedure for its correction. This is manageable, of course, but not ideal. So at this point, I had in hand an approach that led me to some great leads and business understanding of the problem, but didn't perform very well, and another approach based on recent research in the field that performed much better, but was detached from the business problem I identified. Different label shifts, if at all, at different types of positive labels. I decided to go back to where my journey started and try to find a path that would better fit my needs. At this point, what I wish to find is a way that would combine the advantages of the two approaches, using the business understanding I've gained and combine it with known approaches. I was also hoping to find an approach that would help me reduce complexity in production environment and would be easier to maintain the model I eventually develop, own it, and in the future explain it as well. What I decided to do is estimate the new label distribution as suggested by recent research, but this time do that per scenario I identified, or in our COVID example, per age group and background disease, and so on and so forth. Additionally, I did not use these estimations to correct my original model's prediction, but added this intelligence to my model as features. So I basically added features to the model indicating what my estimation is for the new and most recent label distribution among the different subpopulations or scenarios. This means that in this approach, comparing to the previous one I examined, I aim to teach my model to adjust itself to label distribution shifts as part of its training process, rather than performing a correction to my regularly trained model when a shift occurs. So in order to use this approach in production, I will obviously need to productionize this intelligence as features calculated real time for my model's usage. I was hoping that the model will learn to adjust itself and predict COVID As an example, with higher probability for subpopulations in which COVID is actually more common without overestimating it for others. And if we go back to my fraud domain use case, this time this approach managed to provide the improvement I was looking for, both for the known distribution and for the unknown label distribution shifts. To conclude, if you could take one thing from this session, don't surrender to the real world's unknowns. Don't surrender to the real world's unknowns and what it has planned for your model. Try to prepare your model at advance for these unknowns. We saw that it is very common for our models to meet different reality in production environment comparing to the reality presented to them during development. Many of us see it in our day-to-day in various domains. And the scenario presented here today, label distribution shifts, were the ones causing me so much trouble. By examining approaches detailed here today, and specifically by adjusting approaches I read about to my understanding of the problem, I was able to help my model be much more robust, heading towards future label distribution shifts. Obviously, the approach that outperformed others in my use case is not necessarily valid to all use cases. It should be examined separately and treated according to your understanding of your domain and model's real world surroundings. But if you'll be more aware of what could potentially challenge your model in production and keep in mind approaches such as the ones detailed here today, you could really boost your model's performance and make it much more robust to changes it might, or more precisely will, meet in a real world setting. Thank you very much for listening. I'd love to take your questions and chat more about this topic. So please feel free to reach out at the chat or breakout room or offline later on, and we'll discuss this further. Thank you very much.